Afternoon tea. I've been asked to make this the shortest introduction possible so we can get into the presentation. So this afternoon, it's a pleasure to have Tim Ansell speaking. You might remember him from such projects as the hardware that runs all the video stuff at this conference. So please welcome Tim for his talk.
Hi everyone, I'm Tim. You can contact me on Twitter with @mithro. If you want to see these slides, that is a link to it. PyHW, PyCon 2017. And the project I'm mostly going to be talking about is the HDMI to USB. And I've got 107 slides and 30 minutes to get through them. So this is going to be fun. I'm going to talk very fast for some of it. So maybe if my slide would go to the next one. So I love Python. I might have started at a conference about it, and I really love Python, but I'm also practical. I think that you should use the right tool for the right job. Not everything is a nail. And so a couple of years ago, I would have not said that Python was the right choice to do FPGA hardware stuff. But now I say yes. And this is the story of why you should as well and how it's going to make you more productive. And this slide here is to remind me to stop and take a drink. So story time. So I created a free software project called TimVideos. The URL is timvideos.us, so timvideos.us. I'm very creative with naming things. And its aim is to record and live stream conferences. So this is what a recording and live streaming of a conference setup looks like. You've got a mixing station back here that actually runs Python. We have some capture systems up the front and up the back. They run Python. We have a streaming system in the cloud. That runs Python. We have a website that runs Django, which is Python. And at a conference like this, the presentations are on Python, and some say even I'm on Python. But there are two things that I didn't point out, and they're these capture hardware. They might not run Python. They do now, but I will explain how we got there. So what we want to do is capture the slides that are on the screen. And to do that, we basically put a box in between the presenter and the screen and basically do a man-in-the-middle attack of their video. And so we developed some hardware to do that. It appears as a webcam and a serial port. The webcam has the presentation video, and then we pipe it into whatever capture software we want. We also have a serial port, which gives us all types of very interesting debug information about what's going on in the system. And that allows us to tell what's going on, like is the presenter sending the wrong resolution, or is the cable dodgy, or any of these type of things, without having to just guess. We can actually know what's going on, which is really cool. The whole system is based around FPGA. And FPGA are these cool things that make hardware problems software problems. And software is really great in that you can make a mistake and you can fix it later. When you make a mistake in hardware, you either live with it or you do a product recall and huge hassle and all these type of things. Whereas with FPGAs, you just fix the description on the hardware, send out an update, and you get new stuff. You also get new features. And so that's really good. The two major languages that are used to program for FPGAs are Verilog and VHDL. You might notice something that neither of these are Python. However, I did say I was practical, and most people use these tools. So it's generally a good idea to go with what the most popular solution to a problem is, unless there's a very, very good reason otherwise. And at the time, we didn't have a good use case about why we should be special, why we shouldn't use the tools everybody else was using. And so we decided to make a choice of developing the firmware for the FPGA in a mixture of VHDL and Verilog. And we had it mostly working for this board here, which is the Digital Atlas. But it took us 3 years. We only had a basic set of features. We didn't have things like Ethernet support or buffering or any of these really more advanced features we want to support. And the licensing around the VHDL and Verilog we were using is complicated. We were using some Verilog and VHDL that was automatically generated by the FPGA vendor, and technically their clause says you can only use it on their hardware. I mean, most of the time it only makes sense to use it on their hardware because it uses specific, it's optimized for the way their hardware works, but it does mean technically it's not open source. If you can't reuse the code on a different piece of hardware, that's not open source. So complicated licensing. And then I decided to make my own hardware because I wanted my hardware to be open source and anybody can make copies, modify it, change it. And so we developed our own open hardware. It's very similar in design to the commercial Atlas board we were using, but it's not identical. And it's different enough in that it has a bunch more features that we would have loved to have on the dev board, but it's a dev board. It's not specifically designed for us. It has expansion capabilities, and it has some high-speed stuff. And it's very similar, but it's different enough that it's not identical. We can't just run the same code on both of them. And both Verilog and VHDL make it quite hard to have this type of specialization where you have two very similar things. So you want to share a large amount of stuff, but you want to have some type of customizations. And those customizations may run quite deep into the system, like the data width of something might be 16 bits instead of 8 bits. And that runs throughout the whole system. And you don't want to have to rewrite your system to have an 8-bit version and a 16-bit version. You just want to be able to adapt to the width and things like that. So we were in kind of a quandary. It'd taken us a long time. I was getting nowhere. I was getting demotivated. And I came across this. This is the Mixio. It had a very similar design to our board. And if you've ever heard of this idea of convergent evolution, or the time, like at certain points in time, an idea is right, this is kind of another proof of this, because I'd never seen this board before until after I've designed the hardware, and it looks almost identical to the way we designed our hardware. It had no capture, and these guys were crazy. They decided they were going to write all their FPGA stuff in Python. They had a HDMI core, they had a DDR RAM core, they had Ethernet, and they only supported 20 boards. And so I was a bit skeptical. There wasn't a huge community, they were a small group. How could such small group of people do something using a tool that nobody else uses and have this thing? But I thought, why not try Python? I like Python. I'm skeptical. And so what I did is I have more money than time, and I contacted this guy called Florent who runs Enjoy Digital and contracted him to use the Migen and stuff to replicate our current existing functionality using their technology. He had already done this technology and used it quite frequently, and he was happy to take my money. And in 4 weeks, he totally replicated our existing setup with a whole bunch more features than we had previously. And this kind of blew me away. It had buffering. It supported both our boards. It had a SoftCPU internally. It had Ethernet support. And so in the end, we had a system which had 4 weeks of full-time development, but only 4 weeks that we'd paid. That was Python-based. It had truly FOSS licensing. It used no vendor generated stuff. Everything they generated themselves, including like the DDR-RAM. Supported multiple boards, and it was like really good. Whereas our previous attempt, was VHDL and Verilog based, and it was hard to extend, questionable FOSS, and it had taken us years to do. So that was really good because it allowed us to use it in production, and we're using this board right now. It's recording this talk, it's recording the other rooms. We've still got a lot more awesome stuff we'd like to do. Like I said, FPGAs make hardware problems, software problems, so we can continue to improve it. And that's going really well. It's being used at PyCons, it's being used at linux.conf.au, it's being used at DebConf. It's used at PyCons in the US, around the US. Not the big one, but lots of the other ones like PyConAU. And so that's really good. So in summary, the story we had was creating this hardware is hard, but by switching to this Python-based, we got more functionality in less time, and we actually had a system we could use at the end of it. So go Python. But if I was you in the audience, I'd be skeptical. Like, why did this happen? And that's what the rest of my talk is going to be about. Why were we able to do this, and why have we been so much more productive in a Python-based system than we were in a VHDL Verilog system? So let's dive deeper, and let me convince you that the reason this is good is partly a Python reason, but also the things that the way we worked and the way the system connected together enabled us to accelerate our development. And so why is it hard to do FPGA development? The first one, and this is particularly that I find frustrating, is that hardware description languages like Verilog and VHDL have been around quite a long time. And a lot of the features and development of them happened before we kind of learnt how to do object-oriented programming and other things like test-driven development and modern CI things. The next thing is that writing hardware is actually hard. It's kind of there in the name. It really matters, like, a lot of hardware, if you get one single little bit wrong, it doesn't work. You don't get any debugging. You don't get any information about what happened. It just doesn't work. And that makes hardware really hard. As well, FPGA toolchains are, to be kind, slow. They're kind of big proprietary toolchains that are extremely frustrating. And so that anytime you have to touch an FPGA toolchain, you are sad. And so how do we solve the problem that HDL languages are old? Well, what we do is we create a language that lets us generate one of the old languages, but lets us talk and think about things at a high level, and then generates all the nasty old code. And so this is what this Migen thing is. It doesn't convert Python. You can't write Python code and have it run on FPGA. What it lets you express is hardware concepts using Python, and it then generates Verilog and handles interfacing to the proprietary toolchains, like running through the steps that it needs to convert the Verilog into something you can load on the FPGA. Then they have this thing called MiSoC, which is basically a library of modules that you can hook together. And MiSoC is really what enables us to get a lot of things done. But the reason MiSoC is really easy to use is because the interfaces are defined up at Python level rather than down at Verilog level, which means we get a very easy system to hook together because Python code, like you've all used classes in Python. That's very easy to understand. One quick thing is Florent Enjoy Digital has a compatible fork of MiSoC called LiteX. So you'll hear me use them interchangeably. Florent has a more generous interpretation of what features should be added and what features should be removed. So we generally use LiteX because it's got a lot more experimental stuff that most people wouldn't consider stable yet. And so that's why we use that. The thing with the Python HDL is it needs to end up on the FPGA. And the way we do that is by generating Verilog. And so you can think of Migen as an easy way to generate Verilog. And so this is kind of what the code looks like. This is a combinational statement which says that A is always equal to B. You can think of it like connecting a wire between the two. And synchronous is basically any time the clock edge changes, A is set to B. So a simple blinking LED. This is what the Python code looks like. You've got a simple synchronous counter that increases on the clock edge. And then we set one of the high bits in the counter to an LED using a combinational statement. And so this is really powerful because Python is a powerful, modern, productive language that we're all used to. And we can also generate the exact Verilog we need. For example, our memory controller core supports SRAM, DDR, DDR2, DDR3. But it produces the minimal amount of Verilog where for the DDR3 output, if you select DDR3, or if you select DDR2, you get the DDR2 version. But you don't get both in the output. You only get the minimal Verilog needed. So other things like we can basically say that our counter and have our signal automatically sized to the number that we want to put in there. So this basically makes our counter, we can change how fast the LED flashes by changing how many cycles it would count to. We can also do things like for loops. So we can say, have it pass in a list of LEDs and flash all of them. This is really hard to do in Verilog and VHDL unless you use some of the more modern features of Verilog and VHDL. And I always found it impossible to understand the Verilog and VHDL versions. And so the solution is we use Python to generate HDL, and that's how we solve A. But that's not the only thing we do. And I'm rapidly running out of time. So I'm going to have to talk quicker. So the other thing is writing hardware is hard. While we've moved to Python, we still have to understand hardware. We still have to write hardware. Hardware is really hard to debug. It's not great. Software is much easier than hardware. So what we do is we try to reduce the hardware that we write. And we only write the essential pieces of hardware that we need. And instead, have a soft CPU inside the FPGA that can run code, normal C code. So we do less in the FPGA by pushing the problem up the stack. And we can write most things in C. And how many people here understand C? How many people here understand Verilog? So just for the video, there are like 2 people who understand Verilog and like 30 to 40 people understand C. So it also means more people can write the C code and debug the C code and understand the C code. We compile GCC. Everybody's probably used GCC if you've done the C code. And we can update it easy. Every time we update this C code, we can load it onto the FPGA without having to reprogram the whole FPGA. And that means that we can update at a much better cycle. The updation cycle for this firmware, we can TFTP load it, and it will take like 5 to 6 seconds to upload the firmware, compared to many minutes to do FPGA stuff. So MiSoC gives you a SoftCPU. The other cool thing is it's agnostic to the SoftCPU architecture. It has a multiple choice. You can change one variable, and you change from the LM32 architecture to the OpenRISC 1K. And it also has a common set of systems for exposing features of your hardware to the CPU, and it generates code stubs for you. So we have a generic GPIO CSR register object in MiSoC. And so this is what your Blinky example looks like. We just create a GPIO out register and say, connect it to the LED. And then we write some C code. We get an automatically generated function that we just call 0 to turn the LED off and 1 to turn it back on. It doesn't matter where the code decided to allocate this in the memory or anything like that. We just call a function, and people kind of know how to call C functions. The real example of this is that we have a SRAM DRAM controller. The initialization for the DRAM happens once at startup. It's a reasonably complicated thing to do, and it's much easier to understand this in C code than it is in Verilog or VHDL code. And we only need it once, so we can load it into the FPGA at the beginning, initialize the RAM, and then do something else useful with the SoftCPU. It has some downsides. You do need a compiler and bin utils. As a smaller community around these architectures, because these architectures are basically designed for FPGAs, and you're writing C, which is not Python. So I have a project to put MicroPython on FPGAs. So we can run MicroPython on the SoftCPU, and we'll be hacking on that at the sprints. You can go to that URL and find out more, and you should find one of these 2 people or me if you're interested in hacking on that. It's mostly C at this stage, but definitely once we get it, we've got it like basic UART and all that type of stuff running. So yeah. So in summary, the way we solve hardware being hard is we do less of it. And that accelerates our development again. And now I've got 5 minutes to go through another one of these. So FPGA toolchains are slow. FPGA toolchains are slow because they're actually trying to solve a hard problem. They take your description of some type of hardware and then try and map it onto the internals of the FPGA. This is in some way similar to a traveling salesman type problem. It is not generally solvable. And the more description you have that has to fit on there, the harder job it has. And so the more code, the slower the compile. And when I say slow compile, I mean industry people are quite familiar with compile times in the orders of hours. So what's inside our FPGA? This is kind of what's inside our FPGA. We have a CPU, a bus that connects things, some memory interfaces, and then a peripheral, or peripherals. That's a lot of code, and as I said, more code means a slower compile. So one thing we've already done is we've moved as much of the hardware code as we can into the SoftCPU. That means the FPGA toolchain doesn't need to see that. And that makes the compile faster. But it's not the only thing we do. So looking at this, most of the time when developing, we're developing a new peripheral, new HDMI thing. We're not developing new CPU or memory controller. And there's this kind of thing off to the side, the computer that you're running things on. And so you kind of see that we have two CPUs here. So what happens if we got rid of the CPU on the FPGA and just used the CPU on the developer's computer? And so that's what we do. We have a bridge interface which basically lets us run the code on your computer and access the hardware in the FPGA like you're the CPU on the FPGA. We have multiple ways of doing that. We can use a UART, or we can use Gigabit Ethernet, or we can use PCI Express. I've got 5 more minutes. And so that CPUs aren't small. Our CPU is actually very resource efficient and quite small compared to most CPU implementations. But it's still another chunk that we've moved off the FPGA. And the bridge implementations are extremely small compared to a CPU. So that saves a lot of resources, and hence we get much faster compile times. But if you're looking at this, what we normally care about is just one peripheral, and we've still got a lot of other stuff here. So let's get rid of all that stuff as well. And like, we only care about one peripheral at the time we're working on. We don't care about the fact that the Ethernet core might work while developing the HDMI core. We only care about, we're working on the HDMI core, let's concentrate on that. And so we go even further, and we cut back basically the whole system to just the peripheral that you're working on, the bridge, and the bus that connects the whole thing, and then do as much development as we can on the developer's computer rather than in the FPGA. And so this makes compile times, which FPGA toolchains are bad at, in the order of minutes instead of in the order of hours, because the FPGA is very uncongested and has much more leeway in how it lays out things. And so less code means faster compile times. The other thing is that we have Python on our developer computer. And so we have a Python API that we can talk to the bridge in. And we can do things like read and write registers over whatever interface exists, like where this code is agnostic to whether it's by UART, or whether it's by Gigabit Ethernet, or whether it's by PCIe. And it lets us just write directly onto the wishbone bus the registers and read the registers. So this makes it really easy to debug, because you're like, why isn't this hardware working? Read a register and see the value. Oh, wait, that value doesn't look at all like what I expect it to be. And so that's really powerful. And we can do things like look at the memory map, or this is like in our blink LED example, this one here would turn on the LED because it writes to the LED GPIO register. And we get things like tab complete. We can see what registers are available and the names that they were given in our code. That information is normally lost when you do FPGA development. You just know that because somebody said so, that this location is where the register is. And if it moves, you spend hours debugging, going, why doesn't this code that used to work not work now? Oh, it's because somebody moved the UART from 02000 to 04000. And they did that for some good reason, but they forgot to tell us, and now we spent hours debugging something that we wouldn't otherwise. So instead, we can just use like wb.regs.uart instead. So in summary, FPGA toolchains are slow, so we try and work on very small bits at a time. It also makes it easier to debug because there's less interactions going on. And so summary of summary, how we're so much more efficient than a lot of people in this area is that we use a Python HDL, we reduce the amount of hardware that we write, and we work on small bits at a time. And most of this power comes from the Migen, MiSoC, LiteX things. The Python HDL is Migen. It gives you the SoftCPU, and it gives you these bridges which allow you to cut back what you're developing on at a time. Another thing I haven't mentioned here is it gives you a very good internal scoping tool that has a Python interface that uses just the bridges to talk about. And that would be number 4 if I had more time. So all the stuff I'm working on is open source. We would love you to be involved in it, and we would love you to come and help hack on it. We've tried to make it as easy as possible to set up. You have to install if you want to work on the FPGA side of things, you have to install the FPGA toolchain, which is a bad experience. Sadly, because it's proprietary software, I can't do anything about that. But if you just want to work on the firmware side of things, as of like 2 hours ago, you no longer need the FPGA toolchain. So that's really good. You can use a pre-built firmware for your FPGA that we have as part of CI. And there's so much more we could do with your help. And I have a tendency to send people hardware who help me. So if you're looking for a new FPGA board, maybe send me a few pull requests, and I'll see what I can do. There are definitely people in audiences who have gotten hardware from me in the past. And I should have told them that this has audio. Let's see if this works. Where's the plug? Am I going to blind them with the sound? Or deafen them? And so we'll be at the sprints. This is a video I made a long time ago. Which apparently the internet doesn't like.
Sprints are awesome! If you haven't been to a PyCon sprint before, you should definitely try and make sure you stay for the next one.
The sprints are great because they don't just let you put a face to a name, they let you put a person to ideas that you're working with.
Sprinting is an excellent way to get everyone together, especially new contributors.
We have, I think, a half dozen or more people who have already, submitted patches, gotten tickets closed out. This has been tremendous for us, and beginners keep you honest about how good your documentation is, about how good your new contributor guidelines are. So we've been really excited to see all of these new people here at PyCon.
I'm going to rush out there because there's a lot of code to do. See you later.
Sprints are awesome!
PyCon in the US. We have sprints here after this PyCon. We'll be there hacking on this hardware, and I've got a lot of hardware here that you can come and play with, look at, figure out what is going on. And I also have a couple of laptops with the stuff pre-set up if you just want to understand how this workflow might work. And this is kind of what happens when you get your hardware wrong. So I'll leave that running, and I think we're probably out of time for questions. But I will be around, and hopefully you won't get a problem like this.
Thank you very much.
Thank you.
All right, we've got a slightly less than 10-minute break to the next speech, so I encourage you all to stay.